Hello, Makara?
Yes, sir. Yes, sir.
Can you hear now?
Yes, clear, sir.
Yeah,
I can
okay,
see the
okay.
screen now.
We have a problem with internet connection, so I just got connected with my 4G. Let's see how it works. If you cannot hear well, or if my voice quality is bad, let me know. Maybe I'll continue later, okay? Okay. I just figured out. So we were talking about again this determinants. It's not so complicated, you know. If you just know these properties, you will see that we can compute any determinant very fast. And we're talking about the last property here. It says that if B is obtained by adding a multiple of one row or column of A to another row. So yesterday also we did this, if you remember here, if you're given this determinant A, B, and C, D. And you can just obtain another matrix, for example, I can just multiply, for example, the second row by K and add to the first row. What do we have here? Here we have A plus K times C and B plus C times D. Not C, here we have K and here we have C, D. What happened here? We obtain new matrix, right? How? By applying this elementary row operation, by just multiplying a row. I'm not saying elementary row operation because here also it works for the column. That's why we're just not saying that elementary row operation, because row operation means we are actually doing the operations on the rows. But here, also for columns, it works. Here, if you multiply, for example, the second row by constant K and add it to the first row and evaluate the determinant, it's saying that here, determinant of A, we just write using this parallel bars. Here we have determinant of A will be equal to determinant of B. Even if you can just do like this, for example, if you multiply the first column by K and add to the second row, also actually this will be the case. Let's say, how about if you obtain like this? Here we have AC, multiply the first column by K and add to the second column. So it is B plus KA, and here we have D plus KC. And also it's saying that determinant of B is equal to determinant of A. Okay, now let's just use those properties to do these determinants. Here, using a row reduction to evaluate a determinants, computes the determinant of A. Okay, row reduction. But here, for example, let me just do it here, determinant of A. What is it? Actually, it is the same as, for example, here we have 2, 3, negative 1, 0, 5, 3. I'm going to use the last property. The last property says that if you multiply a row by constant and add to any other row, the determinant doesn't change. So here, if you just multiply the first row by 2 and add to the last row, 4 plus negative 4, it is 0. 6 plus negative 6, it is 0. And negative 1, here we have negative 2 plus 2, that's equal to 0. What is it? If we just, here we have 0 row right here, because it multiplied by 2, 0, 0, 0. So we know that using the first property, if any matrix contains a 0 row or 0 column, its determinant is equal to 0. And how about B? How about B? Determinant of B is equal to, for example, I want to create one more 0 here, or, okay, good. So here we have 0, 1, 5. Okay. First, let me multiply the third row by 1 and add to the second row. What happens here? Here we have 5, 6 plus negative 6, it is 0, and 1 plus 9, here we have 10. And here we have 2, 6, 6 and 1. 2, 6, and 1. So now, as you see here, in the second row, right, and 5 is a common factor, I can just take this out. Here we have 5 using the second property. That is, here we have 0, 1, 5. Here I have 1, 0, 2. And here we have 2, 6, 1. Can I simplify this further? Yes. I can actually have one more 0 equals 5. And here we have 0, 1, 5, and 1, 0, 2. Let's multiply the second row by negative 2 and add to the last row. Negative 2 plus 2, that's equal to 0. Here we have 0, so here we have 6. Negative 2 times 2 is negative 4 plus 1, it is negative 3. Okay, now here in the last row, 3 is a common factor. I can just write it as 5 times 3 times, here we have determinant 0, 1, 5, and 1, 0, 2. Here we have 0, 2, negative 1. Okay, so actually we can evaluate this. The first column, if you just compute this determinant by cofactor expansion along the first column, what do we have here? Here we have 5 times 3, that is 15. And here we have, okay, it's plus minus plus, so this will be times negative 1, right? And delete the second row and the first column. What do we have here? Here we have 1, 5, 1, 5, and 2, negative 1. 2, negative 1. It's just 2 by 2 matrix. Here we have negative 15. 1 times negative 1, it is negative 1. Minus 10, it is minus 11, which is equal to 150, 165. Okay, that is how we use the property of those determinants. Using column operation to evaluate a determinants. Compute the determinants if of matrix A if. So column operation, because we are not actually so familiar with this, that's why let's practice here. So determinant of A is equal to, so the column here we have 3, 6, negative 5, 1 to 7, 7, 6, 3. So which one should we, okay. So here, as you see here, if you just multiply the third column by negative 2 and add it to the second row, what do we have here? Here we have 1, 2, 0, 7, and 0, 0, so nothing changed here, 0, 7, multiply by negative 2, negative 6 plus 6, that's equal to 0, and negative 2 plus 3, that's equal to 1. And here we have 0, 0, 3, 1. And here we have 3, 6, 0, negative 5. Okay, so as you see here, the second column, okay, not the second column. So can I create more zeros here? How can I do that? Okay, okay, no needs. So here, the third row, as you see here, the 3, right, it's a common factor. I can just take this out. And here we will have 1, 0, 0, 3, and 2, 7, 0, 6, 0, 0, 1, 0, 7, 1, 1, minus 5. So now if you compute this determinant by cofactor extension along the third row, just here 0, 0, only here we have 1. Actually, I think we can reduce the order of this matrix, right? So here is 1. So here by this column, right, here it is plus, minus, plus. So here we have plus, minus, plus. So this will be plus, just 1. Okay, times, and delete the third row and the third column. What do we have here? If you just delete this, what do we have here? 1, 0, 3, 2, 7, 6, and 7, 1, minus 5. Okay, so now actually I can create more zeros here. For example, if you just multiply the second column by 5 and add to the third column, here we will have 3, 1, 2, 7, 0, 7, 1. Here we have 0, so here we have 3. Multiply by 5, 35, plus 6, it is 41. Multiply by 5 and add this is equal to 0. Right? At the same time, actually, I can just multiply the second column by negative 7 and add here, also actually here, negative 7. Okay, yeah, let me just write here, no problem, since we are just practicing the properties. So here, multiply the second column by negative 7 and add to the first column. So here we have 1, negative 7 times 7, 7 times negative 7, that's negative 49 plus 2, negative 47, and negative 7 plus 7, that's equal to 0. Here we have 0, 7, 1, and here we have 3, 41, and 0. Okay. So now if you just evaluate this determinant by cofactor expansion along the third row, because it has two zeros, right? Plus, minus, plus, plus, minus. So this will be -1. And we should just delete this column and this row. What do we have here? So we have 2 by 2. 1 is 3, -47, and 41, which is equal to -3 times 1 times 41. 41 minus 3 times 47, 3 times 50 is 150, minus 941, so it's minus 1 is plus 141, which is equal to minus 3 times 142, minus 3 times 2, 6, 3 times 4, 12. We have 1, 3, here we have 426. So this determinant equals minus 426. Also in the quizzes or exams, in case if you are required to show your work, you need to show like this. Okay, compute the determinant of matrix A if. So here nothing is mentioned. Here you can just use any method that you like and just evaluate this. That means that we can just apply that, or is it elementary row operation or elementary column operation? Actually, we don't have elementary column operation. Let's just name so for this. So here, if you just look at this, first here we have 2, -4, 5, right? And here we have 5. So we just try to make as many zeros as possible. So here, okay. And so here, if I just multiply the second column by 2 and add here, actually I can just simplify this. So here, determinant of A, here we have 0, 3, 2, 5, and 2, 0, 4, -1, multiply by 2 and add to the third column, 4. So here we have 0, here we have -3, multiply by -2, -8, plus 5, -3, multiplied by -2, it is 2, 2 plus -3, it is -1. So here we have 5, 6, 7, and 1. Okay, so now what else can we do? Here all are minus. Okay, I can just keep this out. And okay, here I can we can have one more zeros here, 0, 2, 0, 5. And here, okay, good. In the second row, 3 is a common factor. I can just take this out. So here we have 1, 0, -1, 2. And here we have 2, 4, -3, 7, and 5, -1, -1, 1. Okay, I'm just trying to make one more zero here. So, okay. So, if you just multiply this third column, right, the third column by 2 and add to the last column, what we have here, 0, 1, 2, 5, 2, 0, 4, -1, 0, -1, -3, -1, and here we have 5, multiply by 2 and add here, that's 0, multiply by 2, -6 plus 7, that's 1, multiply by 2, -2 plus 1, -1. Okay, so here we have more zeros, right? And okay, 2 zeros, so how can we have 0, one more 0 here? I should just add the third column to the first column, right? Just multiply by 1 and add here. So here we have 3. Okay, I hope it's lost that. Here we have 0. Okay, -1 plus 1, it is 0. -3 plus 2, -1. -1 plus 5, it is 4. Here we have 2, 0, 4, -1. And here, I can just keep this minus out. Let me just put it here in front of 3. Okay, equals 3. So here we have 0, 1, 3, 1. 0, 3, 1, 0, 1, 3, 1. Okay, 0, 1, 3, 1. And here we have 5, 0, 1, -1. Equals -3. So now the second row, it has 3 zeros. If you just compute this determinant by cofactor expansion along the second row. What do we have here? Here we have plus, minus, minus, plus, minus. So here we will have minus 1 times, we should delete this column and this row. So what we have here, this 1 to minor of this determinant will be, factors will be 0 to 5. And here we have minus 1, 4, 1, 4, minus 1, and minus 1. Okay. Equals, okay, here we have 3. And let me just do one more thing here, 0 to 5. Okay, if you just multiply the second row by 4 and add here, here we have minus 1, 4, 1. 4 plus minus 4, it is 0. Minus, we just multiply by 4, 16 minus 1, it is 15. Multiply by 4, here we have 3. Okay, equals, so in the last one, actually 3 is a common factor. I can take this out. Without also this, here we have plus, minus, this minus, it is minus. So here we have 3. And if you just delete this row and column, what do we have here? Here we have 2, 5, and 15, and 3, which is equal to 3 times 2 times 3, 6, minus 5 times 15, 75. That's equal to minus, what is it? It is 3 times 69. That's equal to 207. So it is minus 207. So this determinant equals this. Okay, guys, I think that much is enough for computing determinant. As see here, if you just know those properties, and in a very fast way, we can evaluate the determinants. So now let's talk about determinants of our elementary matrices. As you know, that's what is an elementary matrix. Even you had this question in the last quiz, I think, or midterm. It is just a matrix, right? Elementary matrix is any matrix that can be obtained by applying a single elementary row operation on an identity matrix, right? So here it says that if E results from interchanging 2 rows of IN. But first we know that, actually should know that determinant of IN, that's equal to 1, because we know that IN, identity matrix means all the entries in the main diagonal, they are 1, and the rest of the components are, elements are 0. And since it's just upper triangular or lower triangular matrix, its determinant equals the product of the entries in the main diagonal, which is equal to 1. So, and also using the property of determinants, right? If it results from interchanging 2 rows of IN. If you just interchange, only the sign changes, right? So since determinant of A here, from here, we say the determinant of E is equal to minus determinant of IN, right? Just I. So here we know that's equal to 1, that's why it's equal to negative 1. And if it results from multiplying 1 row of IN by K, then determinant of E is equal to K. So we are talking about something like this, where B, as our elementary matrix is this. Here we have 1, 0, 0, 0. Let's say we multiply the second row by K, 0, 0, 0, 1. And what is the determinant? Actually, determinant, we can just write it as, we can take this out. This K times determinant of, what is the whole thing? If you just take this out, that's equal to I, which is equal to K. And if it results from adding a multiple of 1 row of IN to another row, then determinant of E is equal to 1. It's just the last property of determinants, right? Okay, keeping that in mind, so here we have one lemma. Lemma means small theorem. Let B be an n by n matrix, and let E be an n by n elementary matrix. When you just say elementary matrix, is we have only 3 types of elementary matrix, right? The first one is we just obtain by interchanging 2 rows or multiplying 1 row of identity matrix by K, or multiply a row by K and add it to another row. Anyway, it says that then determinant of EB is equal to just simply equals determinant of E equals determinant of B, right? Okay, so now just take this as a fact, and just using this one, because proof is not so difficult, because here just need to consider those 3 cases. in both three cases, you will see that actually we will have the same thing. Anyway, I'll just skip this for you, but here we will prove this theorem using that fact. Okay, here also we can generalize this. If determinant of AEB equals determinant of E times determinant of B. What does it mean? If I just apply this rule to some, for example, K elementary matrices. Here we have E sub K dot dot dot. Here we have E sub 2, E sub 1, and here we have B. Then that's equal to determinant of E sub K, determinant of E sub K minus 1 dot dot dot, determinant of E1 times determinant of, what is it? Here we have B. In general, actually, it is this, because we are just applying this rule onto this repeatedly, right? For first, you just consider this one as 1, and after that, apply this again and again, we will get this expression. Good. So now this theorem says that a square matrix A is invertible if and only if determinant of A is not equal to 0. So that is maybe the main theorem of this section, actually, of this chapter, subchapter. That is characterization of invertibility in terms of determinants. Because if determinant is equal to 0, that means that the matrix is not invertible. Or if matrix is invertible, then determinant of A cannot be equal to 0. It must be different from 0. Even actually, if you remember when we talk about 2 by 2 matrix, right? So to find the inverse, for example, this one is our 2 by 2 matrix. And when we just find the inverse, you see that in the denominator, we have this expression appears, that is AD minus BC, and which is defined by determinant of A. Because if this happens, then we cannot find its determinant because we don't have 0 division. Anyway, now let's get back to this theorem. So first, here it says that if and only if, right? Here we have two-way implication here. So that means that here, if I assume that if square matrix is invertible, then I have to show that determinant of A is not equal to 0. It's different from 0. So now I assume that A is invertible. A is invertible. Now I have to show that then determinant of A is not equal to 0. And after that, also we have to show that if determinant of A is not equal to 0, then A is invertible. Okay. So now, since we're talking about square matrix, now I assume that this A is n by n matrix. Okay. And let's say this R is a reduced row echelon form of A, right? And if you just remember this, how do we get this R? By applying a bunch of elementary row operations on A, right? So let's say those elementary row operations are, let's say this, E1, E2, and ER. So that means that if you just apply this one, the first elementary row operation, and the second one, and the third one, and rth one, and after that we just get reduced row echelon form of A. And we know that it's unique, right? Reduced row echelon form of A is unique. So that means that here we have ER dot 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 E2, E1, and here we have matrix A that's equal to R, right? Now, if you just take determinants of both sides and using the previous lemma, what do we have here? Here we have determinant of ER minus 1, blah, blah, E2, E1A, that's equal to R. And using this previous one, right, that's EK minus 1 and E2, E1, B, that's equal to this. So using this theorem, this lemma, I can just write the left-hand side as determinant of, let me just write like this, ER, and here we have determinant of ER minus 1, dot, 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 determinant of E1, and here we have determinant of A. On the right-hand side, we have determinant of, what is it? Determinant of R. So now we know that these are all elementary matrices, right? And also, if you remember this theorem, actually determinant of this elementary matrix is either equal to -1 or k or 1. It's never equal to 0. We have only three possible cases here. Either that's equal to -1 or k or 1. And we know that each of this one is not equal to 0, and this one is not equal to 0. Okay, right? And none of them is not equal to 0. So that means that here, for determinant of R to be 0, this determinant of A must be equal to 0. That means that if determinant of A is equal to 0, that means the determinant of R equals 0. Otherwise, if this one is not equal to 0, this one is not equal to 0. Right? So now we conclude that here, so determinant of A is not equal to 0 if and only if determinant of R is not equal to 0. What does it mean? If this thing equals 0, that must be equal to 0. If it's not equal to 0, then it's not equal to 0. Why? Because here we have something like that. We have non-zero number here. Anyway, now we assume that, okay, I will just use this part now. Now I assume that A is invertible, right? Because now I assume that A is invertible. Now I have to show that determinant of A is not equal to 0. If A is invertible, then by the fundamental theorem of invertible matrices, we know that this R should be equal to IN. Because when you just reduce this to reduced to echelon form, it is identity matrix, right? And we know that determinant of R in this case, which is equal to determinant of IN, is equal to 1. And obviously it's not equal to 0, right? And this shows that then determinant of A is not equal to 0. And that is the first part of the proof. And how about the second one? This implication. Now I assume that determinant of A is not equal to 0. Now from here we have to show that A is invertible. Right? So how do we show that? If determinant of A is not equal to 0, then by this, right, also because of this equation and also this determinant of R cannot be equal to 0 because we have this relationship here, right? And that means that this determinant of R is not equal to 0 means this R cannot contain 0 row or 0 column, right? So that means that this R must be I. That's IN, right? So that means that since reduced row echelon form of A is I, that means that A is invertible. Anyway, that is the proof of this important theorem, and some other theorems we'll just try to understand, get some intuition, but I'll not provide proof since we have very short time. So now let's talk about another one, and these easy theorems here. If A is an n by n matrix, okay. If A is n by n matrix, then all right, determinant of k times A is equal to k to the power n times determinant of A. Okay, so now when we just say k times A, right here, again, we mean that, for example, if A is, let's say, we have 1, 2, 3, 4, this matrix, and multiplying this A by K. What does it mean? We should multiply all entries, right? Here we have K, 2K, and 3K, and 4K. Now, if we talk about the determinant of this 2K, I mean K times A, let me just write here, then determinant of K times A equals what we have here. Here we have K, 2K, and 3K, and 4K. Right? if any column or any row has a common factor, we can just take this out. Here, for example, let's say work this column wise. K3, KK is common factor. I can just take this out. What do we have here? 1, 3, and here we have 2K, 4K. But don't get confused with the matrix. It's a determinant. Now here, the second column, also it has a common factor. So I can just take this out. K times K. Here we have 1, 2, 3, 4. And what is this? Just determinant of A. So here we have K squared, and here we have determinant of A. Right? Since actually here we are talking about m by n, actually here K times I can just take this K out. That's why here we have K to the power n times determinant of A. And this is another important theorem. Here, if A and B are n by n matrices, then determinant of A times B is equal to determinant of A times determinant of B. Proof is also important, but it's easy to understand. That's why I'll just keep the proof. Should just use it as a fact. So determinant of A times B equals determinant of A times determinant of B. So let's just use this for this example, and after that you'll have break. And let me see how many slides we have. I think we have a lot. Okay. All right. Compute the determinants of A, B, and AB if, right? So now, if we know the determinant of A and B, we can just get the determinant of AB by multiplying their determinants. Since we know that solution, we know that determinant of A times B is equal to determinant of A times determinant of, maybe actually I should just write like this. Determinant of A, B equals determinant of A times determinant of B. Okay, now from here, what is determinant of A? Determinant of A equals 3 times 7, 21, minus 4 times 1, it is 4, which is equal to 17. And how about the determinant of B? 2 times 11, 22, minus 3 times 7, 21, that's equal to 1. So now if you want to find the determinant of AB, we don't have to calculate this again. Multiply and calculate. So what is determinant of A times B? It's just equal to determinant of A times determinant of B, which is equal to 17 times 1. That's equal to 17. All right, gentlemen, let's have some break. Okay, after 10 minutes or we'll continue. Let me just see if we have any presentation now. Wednesday, 11:30, Ratana. Okay, so I will not be able to teach right now. Guys, I'll make some videos, and as I told you, I'll just upload this in YouTube. You need to watch and practice. It's not so difficult. If you have any questions, just you can let me know. We can arrange a time and have discussion. Thank you very much. See you later. Bye-bye.